So we're starting general equilibrium. Let's talk about what equilibrium is. It is when the forward and the reverse reaction are happening at equal rates. Up until this point, and especially in Chem 1, we assumed all of our reactions went to completion, but actually a vast majority of the reactions are in equilibrium with each other. So in terms of a real everyday example, if I reach 0 degrees Celsius for water, I am in equilibrium with the amount of particles that are freezing, but also the amount of particles that are melting, because we are at the change of state of freezing, melting. So it would look like nothing's really going on, but in fact, you have equal number of equal reactions of freezing and melting at the same time. Okay. We are going to be temperature dependent, just like for kinetics, where temperature affected little k. Temperature also affects, guess what it is? Big K. Okay, we will indicate that reactions are reversible by the double arrow, and that is saying, hey, they're happening at the simultaneously, and they are happening at equal rates. That's how you know that equilibrium is happening. Okay, this is the example. We're going to talk about the equilibrium expression. You've got reactants and products. A and B are going to be your reactants. C and D are going to be your products. And you see that obviously you start out a reaction with more reactants, more concentration of reactants, and little to none of the products. And then as time goes on, reactants are decreasing, products are increasing, and then they level out. And that's where the equilibrium state is reached. Here is our general equation. A plus B yields C plus D. The equilibrium expression looks like, oops, we needed to write that in, sorry. It's in your notes, right? Yeah, whenever I was trying to copy it from Microsoft Word to PowerPoint, it wouldn't put it in. So it should look like this. K, big K, is going to be equal to products over reactants. So C raised to that coefficient, D raised to its coefficient, over, I don't know why I did B first, but it doesn't really matter. So products over reactants raised to their coefficient. When we're thinking about these, especially when they're going to ask us theory questions, you want to just kind of think of it as products over reactants and see how that's going to affect. Like if I make certain adjustments, how is that going to affect the equilibrium constant? Okay. We already know all these things, but just to reiterate, so you can't say I didn't tell you, brackets means concentration. Kc is for concentration. Kp is partial pressure, which we'll talk about here in a second. And sometimes we'll just write K is equal to. K is just like the general term. So Kc means I'm dealing with concentration. Kp means I'm dealing with pressure. When we get to solubility product, it'll be Ksp for solids. And then when we do acids and bases, it's Ka and Kb for acid equilibrium and base equilibrium, to the little sub letters. We can use pressures. That's also in your notes. But I want to make very clear that you understand this. When we're doing Kp, we do not use brackets for pressure. We would put pressure of C times pressure of D raised to their coefficients. You don't even necessarily have to put the parentheses if you don't want to, but do not put the brackets. If you do the brackets, that indicates concentration, and it's wrong. And I promise you someone will do that, and I will count it wrong, and you'll be mad, and you'll say, you knew what I meant. But I'm telling you, do not use brackets for pressure. Brackets always indicate a molarity or a concentration. So I often would write it like this. I would just do PCC times PDD. That's supposed to be a big D. I usually don't even put parentheses just because I don't want to take the chance of doing the brackets. Okay? But you're using pressures there. Okay? So here's the thing about equilibrium constants. You're only going to be using gases or aqueous solutions. They're the only things that appear in the equilibrium expression. Pure solids do not appear. We'll see that in KSP. Pure liquids, as in water, do not appear in the equilibrium expression. Weak acids and weak bases will appear, but that is a different unit. That's acid-base equilibrium, and that's typically one of the more difficult units. That's what most kids struggle with in AP Chem is the acid-base equilibrium. So the equilibrium position, what does the K even mean? Why do we care? The K means a lot, okay? I didn't even mean to do that, K. It's just like normal time. Anywho, so initial concentrations, of course, are going to have a higher, more collisions, faster reactions. But what do we care about K? If K is greater than 1, we are going to be favoring the products. If K is less than 1, we'll be favoring the reactants. If you can't remember that, go back to this general K is equal to products over reactants. And that'll show you that if your K is greater than 1, then you're favoring that you're going to have more products. And if your K is less than 1, then you're favoring that you had more reactants in that equation. So that's always a way to look back at that. If you were forced to explain why K equals 1 is favoring the products, well, then you could show them because of this. Okay? So here we have just a little visual of the K value is very large. And just because, remember, the K is very large doesn't mean that it's kinetically a very fast reaction. So I can have a large K, but it might just be a very slow rate in terms of the kinetics. Okay? So here we go. Write the equilibrium expression for this just to see if you know how. So K is going to be equal to NO2 raised to the 4th. H2O is a gas, so we would include it here. Raised to the 6th. NH3 raised to the 4th. And O2 raised to the 7th. So that's how you would write that equilibrium expression. Not hard.
So water as a product is included, but water as a reactant?
No, water as a product or reactant is included because here it's a gas.
Okay.
So gaseous water would be included, liquid water would not. So if that had been H2O liquid, it would not have been included whether it was a product or a reactant.
Oh, yeah. I guess that's kind of phrased weird.
Only thing,
Okay.
well, it says gases and aqueous solutions are included.
Yeah.
Okay? Water as liquid form, because normally water is liquid form, is not included. Because it's a pure substances are not included. Yes?
So when you say favors the products, it means higher concentration?
Mm-hmm.
Okay.
Yeah, that's what it means, higher concentration. Or if they were to give, the other thing that you could see is if you're looking at a reversible reaction and you see you have a very large K value, then you would know that the equilibrium lies in favor of the products, meaning you're going to have more of that be completed. Does that make sense? Okay. So for this one, we are writing the expression for the decomposition of solid phosphorus pentachloride to liquid phosphorus trichloride and chlorine gas. So first of all, write the equation. PCl5 solid yields PCl3 liquid yields, not yields, plus Cl2 gas. So we want you to write K and Kp. So for A, K would be concentration of chlorine only, and Kp would be partial pressure of chlorine gas. You can put parentheses or not put parentheses around it, but you don't put brackets. And then B is copper 2 sulfate. No, that doesn't have that. Pentahydrate means 5 waters are attached. And it's just going to decompose into 5 water, and it says water vapor, so that's a gas, plus the solid CuSO4. So again, this is the only thing that would appear for K would be your concentration of water, because it's a gas, and Kp, let me be raised to the 5th, would be partial pressure of H2O to the 5th power. There I might put parentheses around it just to show to the 5th power. but do not put brackets. Okay? So now we know how to write it, so let's talk about doing some calculations with it, or what happens if I change it. They like to ask multiple choice questions about these. So if I have some changes to the equilibrium constant, let's say I change the stoichiometric coefficient, so I have a K value for my reaction, and I say, well, I doubled all that, and I doubled my reaction, then I'm going to raise K to that power. So if I doubled it, I would say K to the second. If I reverse it, I'm going to take the reciprocal of K to get what the K value is for the reverse reaction. And then, I'm not sure what happened to the PowerPoint there. It's right on your paper, right? What the heck did that? See, I worked on these at home on my Mac, this PowerPoint on my Mac, and I sent it to myself, and I just uploaded it a while ago, so I haven't had a chance to proofread. I don't even know where that came from. There's no explanation for that. Like adding, how did all that stuff get in there? Okay. And then so you multiply them each other. Okay, K1 times K2 times K3 would give you a K value for the overall thing. So here we have the following equilibrium concentrations. They're saying that they're equilibrium concentrations, so that is good. So we have our reaction for the Haber process, which is the synthesis of ammonia. So it's 1 nitrogen, 3 hydrogen yield 2 ammonia. So calculate the value of K at 127. So let's go and do that. K is going to be equal to the NH3 concentration raised to the second over the nitrogen, and then the hydrogen raised to the third. If you want to take my word for it, that works out to be 3.8 times 10 to the fourth. What is missing from K there that most everything else has? Units. There's not typically a unit for K. All right, so now it says calculate the equilibrium constant, same temperature for this reaction. Well, what did we do for that reaction? We reversed it. So since it's reversed, and we usually say K prime is going to be equal to 1 over K. So 1 over 3.8 times 10 to the negative, not negative 4, positive 4, is going to be equal to 2.6 times 10 to the negative 5. So that's how you make that change. Because it's a reverse reaction, we just take the reciprocal of K. And in the last one, what did we do to the last reaction? We halved it. So we're going to take K raised to the 0.5, or 1/2, but 0.5 is 1. So then we take the original K, 3.8, times 10 to the fourth, and raise it to 0.5. And our handy-dandy calculator should give us this.
So anytime you're writing, like, changing it from the original
Yeah,
value, you write K prime.
Yeah, so you can show how it changes. Okay. Okay? We good so far? General equilibrium is pretty straightforward. You won't struggle to it much. Okay, and then this one, I'm going to pause, and I want you to calculate the equilibrium constant and show that they are the same for both trials. So y'all can do that on your own and practice your own little handy-dandy calculating. FYI, you should write a balanced equation. All right, let's see how you did. Bam. Should have gotten like 4.36 and 4.32. Yeah. So that's close enough to being the same. Okay. All right. So now we're going to talk about how we can relate pressure Kc and Kp with pressure and concentration. I will preface this with the fact that this calculation is no longer on the AP exam, but it does help you to understand the concepts between the two, and they'll still ask about the theory, but they don't give you this equation on the formula chart, so you're not asked to calculate it, but I'm going to ask you to calculate it because I think it's important.
So on the last one that we just did, if we do it in any form, like you can use like fraction coefficients or something like that, and you get that they're still roughly the same, but like they're different numbers, is that still okay or no?
Huh?
So I guess, so the coefficients.
I'm recording.
What?
No, she was asking me if I remember to hit record.
So
So what do you mean the coefficients?
Well, the coefficients of the reactants and products.
We have to balance, the coefficients are
Yeah, so-
your exponents.
Yeah, so I balanced it, right?
Yeah.
But can I use 1/2 O2 instead of doubling everything else? And then my K values are still roughly the same?
Well, but then if you're doing 1/2 like oxygen, then you would need to, when you put it in the equilibrium expression, you'd have to raise it to 1/2.
I did.
Well, then you should get the same answers.
I got different K values, but they're both very close to each other.
But why would you not balance it like a normal balanced equation is what I'm
I
asking.
don't know. I just felt
Okay.
like doing 1/2 O2.
Okay. Okay. Back to this. KC and KP are not interchangeable. However, there is one exact point when they would be equal to each other. And we can relate this equation as KP equals KC, RT raised to the delta N. R, of course, is your gas law constant, 0.0821. Temperature, of course, since we're using the gas law constant, temperature needs to be in Kelvin. And then delta N is your, moles of gas. It is always going to be, when you're calculating this, it's going to be total moles produced minus reacted. Okay? And that's important because sometimes you will have a negative number and you'll be raising it to a negative one, and that makes a difference if you're raising it to a positive or a negative. Okay? Sometimes when kids look at this equation, they can't remember which comes first, the Kc equals Kp or Kp equals Kc, and we can remember it by Pc because we were going to be politically correct. So Pc, Kp equals Kc. It's just called the PC equation, politically correct. So that, okay. So even though it's not longer tested, we're going to do some work with it. Okay. So calculate the Kb value for this particular reaction. It's giving you the balanced equation. So we're going to calculate that real quick. Kp is going to be equal to the pressure of NaCl raised to the second over pressure of NO raised to the second times the pressure of Cl2. So 1.2. Notice I'm using parentheses, not brackets. We have 1. So that works out to be 1920. So in the next one, it says using that Kp value, calculate the value of K. So we're going to use this equation, Kp equals Kc RT delta N. Delta N in this case, if you go back and look, I've got 3 moles of gas going to 2 moles of gas. And then, of course, delta N is produced minus reacted. So -1. Delta N is going to be a -1. Do you get how I got -1? Okay. So now we're just going to plug it all in there. So we have 1920 equals to Kc, 0.0821. Kelvin temperature 25 is 298 raised to the -1. So then I get Kc is equal to 47,000. Excuse me. Okay? Any questions on that? So when, I said there's one particular instance when Kc and Kp are equal to each other, what is it? It says it on the paper.
That's equilibrium?
Nope. When did you say, Adam, say it? You said it back there.
When delta N 0.
When the number of moles are equal to each other. So moles reacted, moles produced equal to each other, then you have equal, Kc is equal to Kp at that point. Okay, the reaction quotient. Bam! This is to use when system is not at equilibrium. It's Q for quotient. Okay. It's calculated just like K, exactly like K, except that we're not using equilibrium concentrations, we're using some other either initial or some point along the reaction. And we can compare Q to K and determine if we are at equilibrium, if we're shifting to the left, shifting to the right. Stand up, sit down, fight, fight, fight. Just kidding. It rhymed. Okay. Q. If Q is less than K, the system is not at equilibrium, and the reaction will shift toward the products so that eventually K will equal to Q. If Q is equal to K, you are at equilibrium, and then if Q is greater than K, the system not at equilibrium, and then you will shift to make more reactants to ultimately reach K. So I promise you they'll ask you questions and have you ask which way the reaction will shift, and you will be comparing Q and K. So, but this is the standard way it's defined, but I'm going to show you an easier way, or a better way, if you will. And instead of comparing Q to K, I'm going to flip them, and I'm going to say if K is greater than Q, I'm going to shift to the right, the way of the arrow. Shift toward products. If Q is equal, then it's the same, so we don't have to worry that. So Q equal K, no shift. And then if Q is less than Q, if K is less than Q, then you're going to shift to the left and favor reactants. In books, it's defined this way. They'll do Q that. But if you flip them, the way of your greater than, equal, less than sign, whatever, is pointing to the way it shifts. So it's just an easier way to do it. So, yeah. Okay? So here we have 3 reactions. Predict which direction the system will shift to reach equilibrium in each of the following cases. So I'm going to, again, pause the video, let you work it. I'll work it while you're not looking, and then we'll come back together. Okay, here is what it should look like. Okay, first of all, you have to write the balance equation correctly. If you, I can't talk. So if you didn't know what it was, like 2 problems ago, we wrote it down. Okay, so calculate Q. In the first case, Q is much bigger than K, so we shift to the left.
Much bigger.
And then in the second case, it's equal, so it's no shift. And the last case, I was running out of room, so I didn't write the actual equation, but you get the drift, and it was less than Q, so Q is less than K, so it shifts to the right, favoring the products. What that means is, as that reaction proceeds, it would form more products until it reached the equilibrium state. Okay? And I believe that is where I want to stop today, because that takes us to rice tables for calculating things when you don't know all the answers. And that's where we're going to need the quadratic equation on occasion. So by Monday, if we can't upload it from my calculator, then y'all need to try to program the quadratic equation or solve it by hand. Your choice.
That's right. Start with this.